All right, our exam is on Thursday, right? You all ready? Ready? Excited? Nervous? We'll talk about it at the end. We'll have a little bit of time. We need to finish off this last topic, which will also be included on the exam. And I have all, everything that I've collected or that I've had you do is in here. So I'm going to pass the folder around, and I'm also going to ask you to sign in. So go ahead and grab your stuff, sign in, pass it on. All right? All right, so last class we were doing these improper integrals, right? 6-6, yes? Are we about to get to 6.6.6? Is that bad luck or what? Do I have that on here? Oh, I do. All right. All right, so last class we were dealing with integrals that had infinite limits. Did I start late? All right, so last class we had functions where our intervals were infinite, right? So we would want to go forever here to infinity and try and find the area under there. Or we could go the other direction forever, or we could go both directions forever. Now we switch gears and we talk about type 2 infinite integrands. In other words, we're going to have discontinuities within the function itself, within the interval that we're looking at. So look at this picture here. Let's say we have a function that does something like this. Let's say we're trying to integrate here from 2 to 5 for this function. Well, at 2, we appear to have a vertical asymptote, right? So we can't actually plug 2 into the function because the function's not defined at 2. But does it still make sense for us to try and figure out what this area would be? Because again, it seems like it tapers off like a funnel. It kind of gets squeezed off, but there's still area, right? Closer I get to 2, right? So it makes sense, like, all right, maybe we can handle this. Well, we can do it with a limit, just like we did the other one. So that's one scenario we could have. Another scenario we could have, I feel like I passed something up. No. Another scenario we could have would be this one, where the discontinuity is at the right endpoint instead of at the left endpoint. All right? So if that happens, can we do it? And lastly, what if we have a discontinuity within the interval itself? So let's say here I'm integrating from 1 to 3 on this function. Is it clear that at 2 it appears we have a problem? Yeah. One of the trickiest parts with these integrals is that if you don't recognize the discontinuity, like if you just miss it, then you just do this integral from 1 to 3 without accounting for the discontinuity, your answer is going to be wrong. And I'm going to show you an example of that, as we move forward today. All right, so 3 types. We have a discontinuity at the right endpoint, discontinuity at the left endpoint, discontinuity within the interval itself. Now, what do you think we'll do with this? We're going to do a limit, right? But for this one, we're actually going to have to split it up into 2 different integrals. We're going to have to do the integral from 1 to 2, then the integral from 2 to 3. Because if you look at just the integral from 1 to 2, isn't that like the first type I showed you? And if we go from 2 to 3, it's like the other one. We're just going to kind of paste those 2 answers together. We still have the same concept of, where is it? Of this idea of convergent or divergent. If we do this and we get an answer that's a number, we say it's convergent. If we get something like infinity or does not exist, limit doesn't exist, then we will say it's divergent. So let's go and take a look at how we will deal with this first case. So here's that first case. It's a little too big. If we have this, our discontinuity being at the right endpoint, that means our discontinuity is at B, right? because b is the right endpoint. We're going to rewrite this as a limit. We're going to replace b with t, and then we're going to let t approach b, and then what's that little negative sign mean up there? From the left. So think about this interval. We're supposed to go from a to b, right? But at b, we have a problem. So what we're going to do is we're going to kind of approach that b from this side. And that's what that little negative means up there. Any questions? All right, and then what about the other direction? If our discontinuity is at the left endpoint, that means our discontinuity is at a. We're going to replace a with t. Then we're going to take the limit as t goes to a. This time with the plus symbol means from the right. So that would be the scenario where we have the problem. The problem is here, right? So we're going to approach a from the right side. And then compute the limits, or the limit, I should say. And then finally, if we have a discontinuity in the middle, right, then we're going to split it up into two. Where do I have that up here? There it is. Okay. So if we have a discontinuity that occurs within our interval, so our discontinuity is in here, then we will split it into two new integrals. Instead of going from a to b, we're going to first go from a to c, and then go from c to b. Make sense? And that's it. From there, we can just get into some examples. All right. Now this one may look familiar, because at the end of class last time, we actually came up with a formula that said that the integral from 1 to infinity of 1 over x to the p dx was equal to two different things. You remember this? It converged or diverged, right? When did it converge?
When does it exist?
There was we had to know something about the p. If p was greater than 1, it converges. And if p is less than or equal to 1, it diverges. And we actually even came up with a formula for what it would converge to. But that was the main result. This problem looks like it, except here we're going from 1 to infinity. Here we're going from 0 to 1, right? I want to just look at this visually, like to make sure you understand the comparison here, that these are not the same things. If I graph 1 over x squared, it looks like this. Okay, that's just the right side of it. Okay, there's another side on the left. But if I go from 1 to infinity, that means from 1 this way, that blue area, finite or infinite? The blue area to the right forever, finite or infinite? It's finite because it converges, right? So it converges to a number because p is greater than 1, because what's p here? Well, 2. This blue right here would be the integral from 1 to infinity of 1 over x squared dx. Understand what I'm saying? So that blue would be finite. What we're looking at now instead, and I thought I had red markers in here. Are there any red markers? There's one. Okay, let's see if any of these work. Thank you, sir. Now here is what this integral is. And it goes up in there, right? There's area up in here. So we're wanting to know integral from 0 to 1 of 1 over x squared dx. We don't know yet, right? Any guesses? Finite or infinite? Infinite? Well, it's going to be one or the other, right? It's going to converge or diverge, right? So just flip a coin. All right, let's actually go through the work, all right? I just wanted you to see a comparison of what we did last time. We went from 1 to infinity. This time we're going from 0 to 1. and we have an issue at 0 that we have to deal with. All right, here we go. So the first thing I'm going to do, and what you should get into a habit of doing also, is go ahead and write down what the function you're integrating is. All right? That function, that's our integrand. That function is discontinuous at what? X is 0, right? 0 would make that function undefined. And we are looking at the interval 0, 1, right? So I like to draw the interval out here, just like a little number line. Here's 0, here's 1. And I do like to circle where I have some problem. So because I'm looking in between 0 and 1, right, I'm going to be trying to integrate in this little region here, and that's a problem. I'm going to need to approach that 0 from the right side. Do you see why I'm not coming in from the left side? Because my interval's over here, not over here. So I'm going to now convert this into a limit. So I write it down first. And now here comes the limit. I'm going to let t approach what? 0, right? And which side am I going to approach it from? Right? So what do I put? A little plus sign. And then I write integral. And I've replaced the 0, right, with t. So from t to 1 of 1 over x squared dx. What do you think the next step is? Go ahead and integrate. What is the antiderivative, right? Let's get the antiderivative of 1 over x squared. So that should be pretty straightforward, right? 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 Negative 1 over x is the antiderivative of 1 over x squared. So here's the notation we use, the bar here, t to 1, like that. Next thing is going to be a limit again, then the brackets, then the 2 sets of parentheses, right? And I'm going to start plugging things in. So I'll go ahead and do that. I'm going to do it over here. So we have limit, t goes to 0 from the right, bracket, parenthesis, parenthesis, and first I plug in 1. What do I get when I plug in 1? Just negative 1 over 1, so negative 1. And when I plug in t, I get negative 1 over t. I could actually take the limit right now, but I'm gonna write a little bit more. Just clean it up just a little bit. I just wanted to put the negatives together and make it a positive. All right, what is the limit as t approaches 0 from the right side of this expression? Did I hear something? No?
Negative 1 plus I think it's bigger.
This goes to
Infinity.
We're going to 0 though. T is going to 0. This number's getting small, right? The denominator's getting small, which means fraction gets big. So I know for my Cal 1 students, the way I showed my Cal 1 students is to think about what's happening here. Your numerator is not moving, right? So I tell my Cal 1 students that my numerator is fixed. In addition to that, it's positive. 1 is a positive number. My denominator is approaching 0. When it's approaching 0, I just need to figure out, is it approaching 0 through negative numbers or positive numbers? Well, I'm to the right of 0. If I'm to the right of 0, these are little positive numbers, right? So I've got a little positive number here. So what I tell my Cal 1 students is, if you ever see in a limit a fixed number over 0, you have 3 options. Infinity, negative infinity, or does not exist. Those are the only things that can happen here. And in this particular case, because the numerator is a positive number and the denominator is also a positive number, the ratio of 2 positive numbers must be positive. So your answer must be positive infinity. The only time you would get does not exist is if this limit was not being approached from the right side, but we actually erase the plus, that means it's from both sides. And if that were to happen, you get two different answers, positive infinity and negative infinity, depending on which side you're on, and that would mean it does not exist. So this is headed towards positive infinity, right? That means this is headed to infinity. Infinity minus 1 is still infinity. This diverges. Questions? Fixed number over 0 goes to infinity, negative infinity, or does not exist. All right, that's it. Shall we do another? All right. We do not need to, someone in my other class this morning was like, when we got to this point, they were like, L'Hopital's rule. You can't use L'Hopital's rule here, because what do you have to have for L'Hopital's rule? 0 over 0 or infinity over infinity. We don't have that. So we don't need it. Well, don't need it, can't use it. All right, next one. All right, so my function, my integrand, is 1 over root 2 minus x. Now that function actually has lots of problems that could, or lots of things that could become problematic for us because it's a square root down there. In fact, if we want to just talk about the domain of this would be a college algebra question. What's the domain of this function? You would need to guarantee me that that right there is greater than 0 and not 0 either, because if it's 0, you have division by 0, right? So if you were asked to find the domain of this, you would just say, okay, I need 2 minus x to be bigger than 0. That way I can take the square root of it and that it's not 0, and then just move things around. Just add x to both sides. That'd be x is less than 2. So on a number line, it's everything this way, right? Not including 2. That would be the domain of the function itself. Yeah? Now, the interval we're looking at goes from where to where? It goes from 0 to 2. So do any of those numbers cause a problem? 2, right? Now, anything to the left of 2 was fine, but 2 itself couldn't be plugged in. So I do have an issue right there. So I'm going to need to approach, with that limit, I'm going to need to approach 2 from the left side. Okay? You don't need to do the domain. I just wanted to kind of illustrate that I can't just say that this has a discontinuity at a single point. There's actually an infinite number of places where this function falls apart, right? Anything from 2 to the right is going to be a problem. And yeah, okay. Integral time. So I'm going to write this down. Integral 0 to 2, 1 over root 2 minus x dx, which I now convert to a limit. T is going to approach what? 2 from the left, so I use a little negative sign. And then I have integral 0 to t, and then the integrand. Okay, so that's our rewriting of things, right? I'm going to move this. All right. Well, we have to integrate, don't we? This one's a little more involved. The integration is a little more involved than the previous one. The previous one was just a power rule. I would expect that everyone could probably get to that pretty easily. Because this one requires maybe a little more work, I'm going to do the indefinite integral over here just to go ahead and figure out what the antiderivative is, and then once I've got it, I'll bring it back over here and then plug in the ends. How are you going to do that? Is that?
Use
U sub, just a basic U sub. U could be 2 minus x. du is negative dx. Let's move the negative to the other side. Negative du is dx, right? And then just rewrite the integral. That would become integral 1 over root u. And then dx is negative du. So how about we put a negative out here and put du like that? And that you could get, right? I mean, like given enough time, that's u to the negative 1/2 and do your power rule. I believe this does come out to be negative